We know that when light hits a boundary between two medium, some of that light is reflected and some of it is transmitted into the second medium. This video will focus on that portion of light that is transmitted. Mainly, this video is going to focus on something called refraction, which is the bending of light as it travels from one transparent medium to another. Let's take a look at an image showing refraction occurring. Here I have kind of a diagram as well as a photo of refraction. We can see here the incident ray and the reflected ray, which we've already learned about, as well as the angle of incidence and the angle of reflection. But now we also have a third beam called the refracted ray. You'll notice that that refracted ray does not follow along a straight line from the incident ray. Instead, that refracted ray is bent. You'll see here in the picture on the right, beam 1 is our incident ray, beam 2 is a reflected ray, and beam 3 is our refracted ray. That light is going from air into some sort of plastic. When beam 3 is incident on that bottom surface, it reflects and makes beam 4. At that bottom surface right there would also be a portion of the beam that would be transmitted. But since the medium below that block of plastic is not transparent, we cannot see that transmitted beam. When beam 4 hits that surface, the boundary between the two mediums, you'll see that some of it leaves the block as beam 5. That again would be a refracted ray. Pointing at from the diagram on the left-hand side, we notice the angle of incidence, theta 1, the angle of reflection, theta 1 prime, as well as a new angle, theta 2. We call that the angle of refraction, or the angle that the refracted ray makes with the normal. Remember, the normal is an imaginary line that you draw in perpendicular to the surface wherever a beam of light is incident on a surface. Let's learn a bit more about refraction. To do math with refraction, we need to know about a value, something called the index of refraction. The index of refraction is a property of a material that is related to how fast light travels in that medium. All transparent materials or transparent mediums have their own unique index of refraction. The index of refraction can be calculated using the equation n equals c over v. N is the index of refraction in this equation. C is a number that we've already learned about, the speed of light. But we didn't learn about the fact that the speed of light, 3 times 10 to the 8th meters per second, is actually the speed of light in a vacuum. Any other medium that light travels through has a speed that is less than 3 times 10 to the 8th. Nothing can ever travel faster than that speed. V in this equation is the speed of light in whatever medium you are in. Notice that we're dividing meters per second by meters per second. That tells me that the units for the index of refraction, or rather, it tells me that the index of refraction doesn't have any units. When I divide meters per second by meters per second, I just get 1. You also heard me mention that nothing can ever travel faster than the speed of light. That means that at the very worst, I'm dividing 3 times 10 to the 8th by 3 times 10 to the 8th. Or, in other mediums, I'm dividing 3 times 10 to the 8th by something smaller than that. That tells me that n is always greater than or equal to 1. A few common indices of refraction that we will use regularly, so it may be useful to have in your notes, would be the index of refraction for air. In air, light travels very, very close to 3 times 10 to the 8th meters per second. And so that tells me that we can use the index of refraction for air to be 1.00. in water, the index of refraction is approximately 1.33. There are other indices of refraction that we will use throughout this chapter, and you can find a table in your textbook that'll give you some of those common indices of refraction. You may need that table for doing some problems either in class or on WebAssign. This index of refraction is important to help us calculate how much something bends when it travels into a new medium. And to actually figure out that value of how much something bends, we're going to use a law called Snell's law. Snell's law tells us that the index of refraction of whatever material the incident ray is in times the sine of the angle of incidence is equal to the index of refraction of whatever material the refracted ray is in times the sine of the angle of refraction. It's important to note here that typically we'll be dealing with angles in degrees, so you need to make sure that your calculator is in degree mode. Without doing calculations, we can figure out exactly how the light bends with this equation. Specifically, if we have N1 being less than N2, in other words, if we're going from a low index of refraction to a high index of refraction, like we would be doing going from air to water, for example, your light is going to bend toward the normal. In other words, theta 1 is going to be greater than theta 2. And likewise, if N1 is greater than N2, so like if we're going from water to air, for example, light's going to bend away from the normal. Or in other words, theta 1 is going to be less than theta 2. We'll see an example of drawing these situations in an upcoming example problem. Before we get to the example problem, we need to learn one more thing about refraction. And that's the fact that there's 3 scenarios for when refraction occurs. So refraction only occurs when, first of all, we need both mediums to be transparent. Also, N1 cannot equal N2. In other words, if our 2 mediums have the same index of refraction, the light does not bend at all. Finally, a very important fact is that refraction does not occur when your angle of incidence is 0. In other words, if your incoming light is perpendicular to the surface, no refraction will happen. However, if it hits the surface at any angle other than being perpendicular to the surface, you will see refraction. Okay, so now that we've learned what refraction is, let's try it out in an example problem. In this problem, we have a ray of sunlight that's traveling into my classroom by traveling through the windows. We're saying the index of refraction for glass is 1.52, and that incident ray makes an angle of 30 degrees with the normal. Our task is to draw the path the light ray makes, making sure to label all the angles. And really, when I say label all the angles, I'm focusing on all of the angles of incidence, reflection, and refraction. In other words, all the angles that I'm going to label must be with respect to the normal. Now, I am going to make one important assumption here, and actually this assumption we know to not be true, but it'll make our lives a bit easier. And that assumption that I'm going to make is the fact that we have a single pane window. In other words, that light is simply going from the air outside to the glass of the window to the air inside the classroom. When drawing these diagrams, we really want to make sure to draw some large pictures so that we can see the beam of light and so that we can easily see the angles and mark the angles in there. So it says that my sunlight makes an angle of incidence of 30 degrees. We know that that's always an angle with respect to the normal. So I drew that in here. And let's draw in that angle, that 30 degrees. Now, we learned that light is commonly depicted by a ray, but if you put an arrow on the end of the light where it's hitting the surface, the picture is kind of messy. I'm going to put that arrow kind of partially through the light here. I also like to label my indices of refraction. We know out here we're in air. In this place we're in glass as it's traveling through the glass to the window. And then that light goes back into the air of the classroom. We said that the index of refraction for air is 1.00. Problem tells us the index of refraction for glass is 1.52. And again, back into air, so 1.00. Now, I want to think about this. This light is going from air to glass. So it's going from a low index of refraction to a high index of refraction. If the light were to go straight through, it would look something like this. But since we know that going from a low to high means that it bends toward the normal, it's going to be more like that. So there's approximately my light beam in the glass. Add some arrows in that beam so we know which way it was traveling. Now it's also important to remember that when light hits a surface, some of it reflects. So we also need to make sure that we draw that reflected beam here. We know, thanks to the law of reflection, that this angle of reflection is also 30 degrees. This angle of refraction is something that we'll need to calculate, which we'll do in a moment here. Let's focus on this other surface. We know that light hits this surface at some angle. I'll draw my normal line in there, right where it hits that surface. And mark that angle that I'm going to need to find. We know that when light hits a surface, some of it reflects. So here's my reflected beam. And some of it refracts. Thinking about that refracted beam, if it didn't bend at all, it would look something like this. But since it's going from a high index of refraction to a lower index of refraction, it's going to bend away from the normal. Now I could keep going with this diagram because you notice how this light beam that reflected off of the glass to air surface hits the other surface as well. I could keep going for quite some time with what would happen with this reflected beam right here. But I'm okay with stopping at this point. It'll be more clear in problems that you're doing on your own as to how many reflections you need to draw. Now, we need to do some calculations to finish labeling our angles. Let's start out by calculating this angle right here. That's my first angle of refraction. Using Snell's law to calculate that. And we always want to write our equation before we do any math with it. And this equation tells me that n1 times the sine of theta 1 equals n2 times the sine of theta 2. We know that n1, which is the index of refraction for air, is equal to 1. So to make my life easier, I'm just going to cross that out. Theta 2 is what I'm trying to solve for. And to do that, I'll start by dividing both sides by n2. So I have the sine of theta 1 divided by n2 equals the sine of theta 2. Now to isolate theta 2, I have to take the inverse sine of both sides. So theta 2 is equal to the inverse sine of the sine of theta 1 divided by n2. Now I get to plug some numbers in. So I'm doing the inverse sine of the sine of 30 degrees divided by 1.52. Making sure that your calculator is in degree mode is really important here, as I mentioned before. When you plug those values into your calculator, you should get 19.2 degrees. That makes sense because that angle is smaller than 30 degrees, and we know that light bends toward the normal as it's going from a lower to a higher index of refraction. So now I can mark the 19.2 degrees in here. Now, because I remember some things from geometry, I remember that this angle of incidence here happens to be equal to this 19.2 as well, because they're alternate interior angles. So I'm going to label that as 19.2 degrees. And also, this angle of reflection, thanks to the law of reflection, is also 19.2 degrees. So I'm left with only one more angle to calculate, and that would be this angle of refraction out here. Let's think about that calculation for a second. This time, 19.2 degrees is my angle of incidence, and 1.52 is my index of refraction. So here I have 1.52 times the sine of 19.2 degrees equals 1 times the sine of the angle that I'm looking for. Well, if I look at what the math I've already done, this n2 sine of theta 2 is the same thing as saying 1.52 times the sine of 19.2 degrees. And we already know that that's equal to n1 times the sine of theta 1, and n1 is 1 again. In other words, if I were to do this math in my calculator, I would find that theta 2 is equal to 30 degrees. That was my initial angle of incidence. We got that same angle as the angle of incidence due to the fact that the light was going from air to glass and then back to air again. If instead the light was going from air to glass to water, let's say, 30 degrees would not be this angle right here. We'll do lots of practice with Snell's law and drawing diagrams like this. I want to point out to you how important it was that we drew a large diagram so that we had room to mark our angles in the diagram. Also remember that every angle you calculate and every angle you measure is always with respect to the normal.